Okay, so closing out chapter 9, 9, 10, go back to looking again a little bit more at Taylor and Maclaurin series. So we start with the theorem. This is theorem 922. So we're assuming f is represented by a power series. Call it f of x is sum of a sub n x minus c to the n for all x on some open interval I. And c is one element of that open interval. Then a sub n, f nth derivative, c over n factorial. And f of x is then f of c plus f prime of c by x minus c plus f double prime of c over 2 factorial x minus c squared plus dot 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 plus nth derivative at c by x minus c to the n over n factorial plus dot dot dot. So that is our theorem 922. So f is represented by some power series for all x on some open interval, and c is one x value on that open interval. So that can make life a little bit easier for us. Yeah, let's see. If f has derivatives, all orders at x equals c, sum from n is 0 to infinity, f to the n of c over n factorial x minus c to the n is the Taylor series for f at c. And as usual, c equals 0 means we're looking at a Maclaurin series. All right, so let's put these to work on f of x is e to the x. As you know, each derivative of e to the x will be another e to the x. So f of 0 is 1, f prime of 0 is 1, f double prime of 0 is 1, f triple prime of 0 is 1, and so on forever. So f of x is then f of 0, x minus 0 to the 0 over 0 factorial, plus f prime of 0, x minus 0 to the first over 1 factorial, plus f double prime of 0, x minus 0 squared over 2 factorial plus etc. forever. So that's how we get f of 0 is 1, f prime of 0, f double prime 0, those are all 1s. 0 factorial is a 1, x minus 0 to the 0 is also 1. So we have 1 plus x plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120 plus etc., etc., etc. Since this goes on forever, this is exactly equal to f of x equals e to the x centered at x equals 0. Another quick theorem. 923, if limit as n goes to infinity, r sub n equals 0 for all x on open interval I, then the Taylor series or f converges and equals f of x. So sum from n equals 0 to infinity, nth derivative at c over n factorial x minus c to the n. So as long as our remainder starts going to 0. All right, so this next one, look at what happens if we have f of x is cosine of x squared. So this is not cosine squared of x, this is cosine of x squared. Now, if we did the Maclaurin series directly, it would start getting a little bit messy. F prime of x be 2x cosine x cosine x squared, my apologies. F double prime of x, then you're using product rule. Keep the negative 2x, differentiate the cosine of x squared. So there's another negative 2x. And oh, my apologies, this is sine squared. I was wondering why that was looking strange. Sine of x squared. F double prime of x, product rule, keep the negative 2, keep the sine of x squared, plus now keep the negative 2x, differentiate sine of x squared, and so on. And the derivatives get messier and messier from there. But if we use our shiny new theorems from this section, we can introduce sort of a temporary function, let g of x equal cosine x. And those, the derivatives, particularly at 0, not too terribly messy. G prime of x, derivative cosine, negative sine. G double prime of x, derivative of minus sine is minus cosine. G triple prime of x, derivative of negative cosine is sine. And then we cycle through it again. G fourth prime of x, we're right back at cosine x. And we just keep cycling through. Maclaurin series, we're of course then interested in what happens at 0. So g of 0, cosine of 0 is 1. G prime of 0 is 0, G double prime of 0, -1, G triple prime of 0, we're back to 0, G fourth prime at 0 is back to a 1. So then we could express g of x as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. So notice the first, third, fifth, etc. is dropping out. Minus x to the 6th over 6 factorial plus etc., etc., etc. So then g of x squared of 1 minus x squared squared over 2 factorial plus x to the 4th squared over 4 factorial minus x to the 6th squared over 6 factorial plus etc. going on forever. So then we just sort of clean that up a little bit. Let me make a little room here off to the side. So then g of x squared is the same as the f of x that they asked us about. So that's 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial plus etc. out forever. And you can call this 224 and 720 as well. So we're just plugging in an x squared everywhere we used to have an x in the previous line. Nice, easier, cleaner way to get there. All right, so next we play around with a binomial series. F of x is 1 plus x to the k power. And let's just look at the first few derivatives of that. So f prime of x would be k by 1 plus x to the k minus 1. F double prime of x be k by k minus 1 by 1 plus x to the k minus 2. F triple prime of x, k by k minus 1 by k minus 2 by 1 plus x to the k minus 3. And hopefully you spotted our pattern from there. So for the generic nth derivative here, we have k, k minus 1, k minus 2, k minus n plus 1, 1 plus x to the k minus n power. So 0th derivative, k minus 0. First derivative, k minus 1. Second derivative, k minus 2. Nth derivative, k minus n. And our first derivative, k minus 0. Second derivative, k minus 1. Third derivative, out to k minus 2. Fourth derivative would be out to k minus 3. So nth derivative, k minus n plus 1. We'll look at the centering this thing on 0, so we'll get to play with the Maclaurin series for this. So f of 0 is just 1 to the k, which is still just 1. F prime of 0 be k. 1 to any power is still just 1. F double prime of 0 k by k minus 1 by 1 to a power, so just k by k minus 1. F triple prime of 0 k by k minus 1 by k minus 2, and then 1 to any power is still just 1. So our f of x for this binomial be 1 plus kx plus k by k minus 1 x squared over 2 factorial is just 2 plus k by k minus 1 by k minus 2 x cubed over 3 factorial is 6 plus, and we'll just pretend that I don't write so huge that I have to wrap this around, but pretend that it's still on the same line, plus our generic nth one, k by k minus 1 by k minus 2, all the way out to k minus n plus 1 over n factorial times x to the n plus dot 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 forever. And this will converge on negative 1, 1. All right, so then we look at the power series for tangent of x, and we'll look at a new strategy for that. So we'll start with f of x equals sine x, and then we'll let g of x be the denominator. So f prime of x, derivative of sine is cosine, f double prime of x, derivative of cosine, negative sine, triple prime, derivative of negative sine is negative cosine, and fourth would flip us back around to where we were. And since we're going to look at the Maclaurin series, we'll look at what's happening at 0. So sine of 0 is 0. Cosine of 0 is 1. Opposite of sine of 0 is still 0. Opposite of cosine of 0 is negative 1. Fourth derivative, we're back to a 0. So if f of x is sine x, then f of x is equal to 0 plus 1x to the first over 1 factorial plus 0 x squared over 2 factorial plus negative 1x cubed over 3 factorial plus 0 x to the fourth over 4 factorial plus dot dot dot. Now clearly these guys are going to start dropping out. So the ones that will sort of survive our cancellation, 1x to the first over 1 factorial, I can shorten that guy down to just call him an x. Next guy would be opposite of x cubed over 6. Now we flip our signs again, x to the fifth over 5 factorial. Now we'll just leave them as 3 factorial. It'll be a 5 factorial minus x to the 7th over 7 factorial. Apologies, I didn't mean to write a giant exponent on the 7 there. Plus x to the 9th over 9 factorial. Plus etc., etc., etc. So then negative 1 to the n. So that alternates our signs. X to the 2n plus 1 over 2n plus 1 factorial. So this gets us the odds. If n is equal to 1, two by 1 plus 1 is 3. So that's our x cubed, the negative in front of it, over 3 factorial. If n is 0, even power, that drops. X to the 0 plus 1 is 1 over 1 factorial, and so on. So we'll do the same thing. We're, remember, looking to eventually play with the tangent. So we'll set up g of x as then cosine x. So g prime of x, derivative of cosine, negative sine. G double prime of x, derivative of minus sine is minus cosine. Triple prime, derivative of negative cosine x is sine x. Fourth prime, derivative of sine, we're back to cosine. And then we just look at what's happening in 0 with those guys. Sine of 0 is still 0, and cosine of 0 is still 1. So in our g of x, we have 1 plus 0x over 1 factorial plus negative 1 x squared over 2 factorial plus 0x cubed over 3 factorial plus 1x to the 4th over 4 factorial plus etc. etc. So here it's the odd powers dropping out. So g of x, we have a 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial, etc. And then our generic term on there, negative 1 to the n, 2n, x to the 2n factorial over 2n factorial. So then the tangent would be sine over cosine. So sine, if you'll recall from the previous page, we had x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial plus da da da. And then, my apologies. I need to start that there. To start it here. Cosine x, recall, then was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So while that one's a little bit messy, what your author recommends is just using some long division on that. So numerator inside, denominator outside. All right, so looking at the first term in each, I would multiply 1 by x to get to x. So we have x minus x cubed over 2 factorial. Then we have plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial and plus x to the 9th over 8 factorial and so on. Remember, we're doing long division though, so once I do the multiplication, I subtract, which changes all of those signs we just wrote down. And I'm just going to do the first few of these. So the x's drop out. We have minus x cubed over 6 and plus x cubed over 2. So that would be x cubed over 3, then minus 1/30 x to the 5th, and plus 1 over 840 x to the 7th. Again, we just look at the first term in each, so then this guy will be an x cubed over 3. So we multiply each of these guys by x cubed over 3. So 1 by x cubed over 3 is x cubed over 3. Positive by a negative is a negative, and x squared by x cubed, x to the 5th, and then 2 factorial by 3. 2 by 3 is 6. Positive and positive makes a positive, x to the 4th by x cubed, x to the 7th, and 4 factorial is 24. 24 by 3, 72. And let's go on about that far. And again, that'll flip all of our signs for us there. The x cubes will drop, minus 1/3 x to the 5th and plus 1/6 x to the 6th. So that's minus 2/6 plus 1/6 is minus, my apologies, that was a 30, not a 3. My apologies. Yes. Yeah, 120 and a 24. So negative 1/30 plus 5/30. So we're at 2/15 x to the 5th minus 4, 3/15 x to the 7th, and so on and so forth. So then tangent of x plus 1/3 of x cubed plus 2/15 of x to the 5th. Clearly that would be our next item at the top here. Plus dot 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 forever. Alright, so some problems to try out in 9-10, the end of chapter 9, 1 through 11 odd, 17 to 35 odd, and 41. And I did want to leave a little hint. Occasionally you'll need the pattern where you have a positive one, a pair of negative ones, a pair of positive ones again, then a pair of negative ones again. If you see a problem that has that, try -1 to the n by n plus 1 all over 2 power. Not something I would expect you to just sort of come to on your own. So that's n by n plus 1 all over 2 power on the -1. If you have any questions, please see me. Otherwise, talk to you next time, and stay safe out there.